moment of inertia with respect to general axis. Now we are able to calculate the moment of inertia to special axis. It's an axis of coordinate system. So we are able to calculate moment of inertia Gx. It's a moment of inertia with respect to x-axis, where x belongs to coordinate system. We can calculate Jy, what is the moment of inertia with respect to this axis y, and Jz, moment of inertia to z axis. So we are able, in fact, calculate moments of inertia of body only with respect to axes, which are axes of coordinate system. And what if we would like to calculate the moment of inertia of body to any other axis, which is not a part of coordinate system? So now I will show you how to do it. So let's define the axis, general axis. We would like to calculate the moment of inertia, so Jq. Maybe, as you know, the axis we define by unit vector of axis q, 0. It's a unit vector, and unit vector is on that axis. We can denote it as a q0, and it's defined by components. So q vector is defined by qx, qy, qz, and coincidentally these components are cosines of directional angles, alpha, beta, and gamma. Directional cosines, or better say cosines of directional angles, so I will write it directional angles. It is alpha q, beta q, and gamma q, where we can see these angles. So for example, beta is an angle between our axis and between y-axis. So beta is here. Gamma q is an angle between q and z-axis. So gamma q is here. And finally, alpha q is an angle between our axis q and axis x. So this is alpha q. And cosines of these angles are components of unit vector of axis. So it's nothing too complicated. If we want to calculate the moment of inertia, we need to point out to the mass element dm by pointing vector, displacement vector. So r has some components like x, y, z. It's a displacement vector. Of elementary mass dm. And as we know, in other cases, when we calculated the arm on which the elementary mass is rotating about, for example x, y or z axis, it was always perpendicular to that axis. So now we must find an arm or lever perpendicular to q axis, pointing to the M. We will do it in this way, that we will make a projection, perpendicular projection of R to q axis. So there is a perpendicular projection of R to Q. So a perpendicular projection is made by dot product. So the size of this projection is R by Q0. It's a dot product of this vector and this vector. By dot product we find this size. What is the size of perpendicular projection to the direction of this vector? And this vector has the same direction as a q-axis. So we have this distance, but we like to have not distance but vector. And how to make a vector from distance? To multiply it by vector which gives to this number vector properties but doesn't change size. So it is unit vector, because everything multiplied by 1 keeps their size. But if this one is a vector kind 1, so we give to this size a vector properties. So now by this calculation I got this vector. This vector. It is vector R by Q0 by Q0. And if we look well, we can find, if we denote this vector somehow, so we can see that this vector plus this vector is this vector. Once again, this vector plus this vector, if it is a vector. Okay, so I can draw it by red color to make a difference. So this is some vector we need. This is a vector perpendicular finally to q-axis, and we can see that this vector plus this vector is this vector. So subsequently we can say that this vector is a q, this vector minus this one, and I will put it down. So we can say that this vector is R minus R by Q0 by Q0. So this is a red vector. This minus this. R minus this. So we found a vector which is perpendicular to q-axis and point to elementary mass. And finally we can say that moment of inertia of body with respect to q-axis is given by definition, general definition. So it is integral over m by square power of this vector. So it is R minus R by q powered by 2 dm. So it is the same definition as in previous cases. So moment of inertia is integral of pointing vector, displacement vector, powered by 2 dm. Sorry. So yeah, this red vector is pointing vector here, powered by 2 dm. So we can continue now. We can deal this bracket expression like this. So I can, it's a curve, but I will continue here. And I can say this is something minus something different. So it is a minus b powered by square. Okay? So it is, you should know this, a square minus 2ab minus b square. And if we have this pattern, we can apply it to this a bit complicated structure. So I can continue. Here a is r, so I can write that it is r square minus 2r by all this. So it is r q0 by q0 plus this powered to 2. So it is r q square by q0 square dm. So it's a q integral, and so we can keep r square minus, and this we can rewrite as 2 r q0 powered by 2 plus r q0, and this is 1 because this is a unit vector, and unit vector powered by 2 is 1 because it's a square power of size of the vector. So it's 1 by 1 is 1 dm. And finally we can rewrite it to this form because there is double of something what is here. So we can rewrite it as a r square minus only 1 r q0. Yeah, it was true if I add this because I forgot to do it, okay? Because there is powered by 2 and there is powered by 2 as well. So now it's true what I said previously. So there is double of something what is here, and it's only 1. And one more trick is applicable here. Something vector powered by 2 is equal to square power of its size. So it lost vector properties and its number because r powered by 2 is in fact r by r. What is a dot product? And the product of a dot product is a number, it's a scalar. So it's a scalar multiplication. So we get it is r square. So I'm going to use this and I will apply to this part, to this term. So it is integral of m r square minus, what remains here? So it is r by q powered by 2 dm. So knowing this, so let's analyze this. So R by Q is what? So R is X, Y, Z, and Q0 is Q0X, Q0Y, Q0Z. So it is scalar multiplication. So it is X by Q0X plus Y, Q0Y plus Z, Q0Z. So it's a product of this and R square. Yeah, what is R square? So it is X powered by 2 plus Y powered by 2 plus Z powered by 2. And if we use this and substitute it here, so we can continue, and also using this, that Q0x powered by square plus Q0y powered by square plus Q0z powered by square is, it is a square power of unit vector, and the square power of unit vector is equal to multiplication of size vector by size vector itself. So it is 1. So we can continue. We can continue here. So it is, if we use all this, so you can try it, but it's some way, it takes some time. So you can accept it as I present it to you, or you can examine it yourself. So it is Jx by Q0x square plus Jy by Q0y square plus Jz Q0z square minus dxy Q0x by Q0y minus dx or yz by Q0y by Q0z. Sorry, there are 2. Minus 2dzx by Q0z by Q0x, and knowing that Q0y is in effect cosine of directional angle, we can continue. So JQ is Jx by cosine square of alpha q plus Jy cosine square beta q plus Jz cosine square gamma z minus 2dxy cosine alpha q cosine beta q minus 2dxy cosine alpha q by cosine beta q minus 2dzx cosine gamma q cosine alpha q. Who is distracted by seeing plus and seeing minus? So because plus minus is minus every time. If I wrote a minus, minus, it could be considered as a minus. Minus gives plus, and it wouldn't be correct. So I use this way. So if I split long equation to several lines with minuses, so every time I write plus and continue with minus, what is very illustrative way how to say that in fact it is minus. So if we consider, so this is final formula, and we can rewrite it. We can rewrite it formula to vector form or matrix form. Okay, matrix form. If we say that we have a vector matrix, the mathematical vector is a one-column matrix. So Q as a vector, mathematical vector, is cosine alpha Q, cosine beta Q, and cosine gamma Q. So then we can say that JQ is Q transposed by transformation matrix by Q0 again. So this is a matrix form of this calculation. So in this way we can calculate the moment of inertia when body rotates about Q.